So what do you get when you mix a funny shape with a spider? You get a funny shaped spider. My name is Hannah Wood, and I'm not actually a comedian. I'm a curator here at the National Museum in the entomology department. And my research interests focus on understanding functional morphology, and so I study the mechanics and anatomy of different spider traits. And I do this taking the evolutionary relationships of these different lineages into account. And this research is getting at the heart of evolution, where we're studying different adaptations that spiders have that make them successful in their environments, and then how those traits diversify. For those of you who want to tune out for the rest of the talk, my 5-word micro summary is funny shaped spiders move fast. So I started working on this family that has a strange name, the Mechis malconiids. There wasn't a lot known about this group, and I began working on them because these spiders look very different than typical spiders. They have this unusual frontal region, and I wanted to know why. To really understand this, we have to compare these spiders to what a typical spider looks like. Shown up here, this is a side view, the legs have been removed, and let's compare that to a Mechis malconiid. So if you look at this frontal region, the Mechis malconiids are a bit boxier, they're more elongate in that area, and the chelicerae, which you can think of as jaws or as mandibles, the chelicerae are also elongated. Now, when we examine typical spider cheliceral muscles, those muscles, the orientation it runs almost vertically. However, I believe the shape of the Mechis malconiid spiders evolved because it shifted the orientation of their cheliceral muscles so that they are running almost horizontally. So the cheliceral muscles here are shown in green and blue. This is not the actual color. This is in fact a 3D model built from an X-ray scan I performed using X-ray technologies. And this technology is important to use because these spiders are so small that dissecting them by hand is very difficult, so we can digitally dissect them using this technique. Now, what does this shift in muscle orientation relate to how these spiders move their chelicerae? Well, for typical spiders, this is looking at the front view of a typical spider, and their chelicerae move in this plane of motion. They just open and close in a lateral plane, which is much different for how a Mechis malconiid moves their chelicerae. They can lift their chelicerae up and away from their body at 90-degree angles, and then in the top view, they have a very wide gape, and they have a very great range of movement. And I wanted to understand how this unusual movement functioned and what they were doing with this. And so I started recording these species with a high-speed video camera. Now, the video that I'm playing here, watch the chelicerae as they close extremely rapidly. And to put this image into scale, what you're looking at, the arrow's pointing to the tip of an eyelash, so these spiders are very small, and this species has a strike duration of about half a millisecond. And that video was being played 150 times slower than how you would see it in real life. Now, this next video has an even greater frame rate of 20,000 frames a second. It's being played 1,000 times slower than what we would see in life. And this is a different species that has a strike duration also of about half a millisecond, so 0.0005 of a second. These are extremely fast accelerations and movements. Using these videos and other measurements, you can make calculations such as inertia, force, energy, as well as just getting speed. This graph is showing some of the variation across different species of Mechis malconiid spiders looking at speed. This graph is logarithmically scaled. On the y-axis, we have speed, time on the x-axis. And what you'll notice is that there's a lot of variation among these different species. What I found is that the fastest species has an average speed of about 20 miles per hour, but amazingly, it's achieving these speeds. It's going from 0 to 20 in 0.0001 of a second. This is an amazing acceleration, and the amount of variation, the fastest species is 100 times faster than the slowest species within this family. Now, when you're a small organism, it's hard to produce these fast, powerful movements, and Power amplification is a way around this. So organisms evolved a mechanism to slowly store energy into a system that then gets released instantaneously, producing these fast accelerations. Think of this like a rubber band that you slowly stretch and then release, and the rubber band flings forward. Now, I wanted to understand the evolution of these fast movements, so I needed to look at this branching diagram of evolutionary relationships, which you see here. And I wanted to know how this trait is evolving. So the black dots that you see are marking where species have evolved these high-speed, power-amplified movements. And what you'll notice in this diagram is that these don't all cluster together in one group. Instead, these black dots are dispersed throughout this branching diagram. And what this means is that this high-speed trait has evolved independently within this family, at least 4 different times. And now I'm currently working on the mechanism to understand the structures that are storing energy. This is part of my current work. So where is this elastic energy being stored? In the muscles or in the clypeal tendons that then, as the chelicerae crank open, then this energy gets released instantaneously. So in conclusion, what I found is that these spiders with a funny shape that we didn't know a lot about, it seems that this shape has given these spiders increased maneuverability of their chelicerae. And using high-speed video, I was able to document these movements that are the fastest accelerations that have ever been observed or documented in arachnids to date. And this study really emphasizes the power of evolution, where we see different species are converging on these similar solutions to solve important biological tasks. Thank you. Any questions? Yeah.
What do these spiders eat that they need to be so fast?
So I haven't done a formal study of this, but I have a hunch. The question was, what are these spiders eating? And this is part of my future research, but these spiders are very cryptic. They're hard to observe in the wild, but in the lab, the very fast species, some of them, they would only eat Columbella, which are common name springtails, which have a very rapid escape jump. So I think the fast species may be targeting springtails as part of their diet, whereas the slower species seem to be more generalists and will eat most of what you feed them in the lab. But this is just my hunch. It needs to be formally tested. Thank you.
Hannah, why spiders?
Honestly, the short answer is I wanted to go to Madagascar. I was working, I finished my undergrad in English literature and I love traveling. I thought, oh, maybe I should get my master's in biology, and I got a summer job at California Academy of Sciences where they had a big Madagascar program, and a curator there said he could send me to Madagascar if I did my master's degree in spiders, and I ended up loving the project and the group. So the question is, how did I first observe this, since these spiders are so small? I first observed it looking at the larger species, and I went down to Chile, collected them, and just started watching them in a little vial, and I noticed this unusual behavior where they hold their chelicerae out and open before attacking their prey. But it was so fast I couldn't see really what was going on, and I started recording them, and then it was years and years of work, bringing species back and recording them with a high-speed camera, and then every once in a while I'd get a specimen that was really, really fast. And I mean, people thought I was crazy when I said, oh, these spiders are fast and they have this trap jaw response, and no one really, I think people thought it was a little weird until I started getting this high-speed data. And then at the end, years and years later, I put it all together, sorted everything to morphospecies, and saw that, yeah, there are distinct, these different species, and they have a range of variation in their speeds. I initially thought, oh, maybe they're all fast, and then I started recording them, and oh, they weren't. Some of them were slow, and I was very disheartened, and then I'd get a fast one, and so it was a very roller coaster. And the question, when the chelicerae smash together, if they miss their prey, they will reverberate, but I think you were asking about if they macerate their prey. No, they don't do that. They just, they inject their fangs and they inject venom into their prey, and then they lower, once the prey is dead, they lower and begin sucking it up with their mouth parts. That makes sense. But I haven't observed them macerating. That question was asked to me by about four of the reviewers on that paper, so good job. And in fact, the reviewers didn't like me calling them trigger hairs, so I took that out of the paper because I didn't formally test for it, but that's something I need to go through the high-speed videos and analyze that, so I don't know, but it is, so in trapjaw ants, my understanding is the nerves, they don't run to the ganglia and then back up to the muscle, they run directly into the muscle, so you can get these faster speeds. Trapjaw ants is a group that is well known, and they've evolved these remarkable, it's a distantly related group that has evolved similar behaviors, so to answer your question, I don't know.